Um, so here's an experiment that you can do to see, and this is a very simple demonstration. So what you do is you close one eye, and then you put two fingers out like this, and you use the near finger. You put a near finger and a far finger, and then you use the near finger to cover up the far finger, and then you close. Then you close the open eye and open the the unopened eye. So you switch eyes, and what's going to happen when you do that is that when you're looking through this eye here, you should see the two you should only see one finger that's covering up, that's occluding the other finger. But when you switch eyes, all of a sudden you're going to see both fingers. And what this demonstration shows you, what it tells you, is that the images, when we're looking at something, anything, with two eyes, the images are going to be slightly different. The images are going to be different. This is demonstrated here in this picture where we have the fingers represented as points in space, and of course when you're looking at it through this eye, you only see one point because there's only one. You can't see this far finger. But when you switch eyeballs and look at the same exact fingers without moving them, and close this eye and open this eye, you'll notice that the fingers all of a sudden appear as 2 points on the retina of this eyeball. And again, this demonstrates that whenever our eyes are focused on anything, the images are going to be slightly different, and our brain uses these slightly different images to compute and give us the perspective of 3 dimensions. Like I said, one of the things that you've done is probably seen a 3D movie, and the way those movies work is essentially that you get a special pair of glasses that gives 2 different images, or I'm sorry, gives a different image to each eye. This is a very simple example here, where there's a greenish image going to one eye and a reddish image going to another eye. Your brain takes those 2 separate images plus all the knowledge that you have of what you're looking at and uses those to compute, to give you the perception of three dimensions. The glasses that you wear at the movies do the same thing. The glasses actually read flickers off of the film that you're watching, and use those to slightly adjust the view of each lens so that you're getting a slightly different picture projected on each eyeball. And since you're getting a slightly different picture projected on each eyeball, it's going to give you that illusion of 3D on the flat screen. So this difference between eyeballs in images is called binocular disparity. So binocular means 2 eyes, and disparity, of course, means a difference. So they're not the same. So binocular disparity. So it's a difference in the images from 2 eyes. One of the ways that we can use to define, or to compare, I should say, the images on one eye and the images on the other eye would be to talk about corresponding points on the 2 retinas. So for example, if I were to show you this pen, and you look at it with both eyes, and you look at the very tip of the pen with both eyes, well, that tip, the tip of that pen, is going to appear on one point on the retina of this eye, and it's going to appear on another point of the retina on this eye. So in that way, you can say, okay, the tip of this pen is on this point, it appears here on this retina, and the tip of the pen appears, wherever here on this point in the retina. And we can use that. We can use that point to reference both images on the retina, and we can compare how the point moves for example, if I'm looking at this pen, right, or if I'm looking straight and the pen is moving, but I'm not moving my eyes, that point obviously is floating across my retina, and we can compare the movement between the two eyes of that point, and that's one of the ways that we can use to compare the two images on each retina. There's an ancient concept that we use to this day. It's called a horopter, and the horopter is essentially a curved area around you where all the objects are in focus, and you don't have to refocus your eyes. So if you're looking, for example, let's say, for example, you're looking at a group of people, right? And there's just sort of a loose group of people, going all the way to the back. Well, if you focus on those people right in front of you and they're all the same distance away from you, that's one horopter. And then if you focus on the people in the back and then look at the people that are the same distance away from you there, that's another horopter. So the horopter is this imaginary circle or sphere around you where everything is in the same focus, right? It's actually an old concept. I think the Egyptians actually came up with it. But the important thing about the horopter is that everything that's in a particular horopter falls on the same points on the two retinas. So if I look at a person that's here in my horopter here, and then a person that's here in my horopter here, they're going to fall on the exact, as I move from that person to that person's nose, for example, is going to fall on the exact same points on my retinas as that person over here. And the person further away, the point that their nose is going to fall at on each retina is different. But if I look at the person next to them, it's going to be in the same thing. So objects that don't fall on the horopter fall on different points entirely on your retina. And the points, if the points are different, that makes different images. So one of the ways that 3D works is that you get a little bit of one horopter in one eye and another horopter in another eye. And that difference makes for different images. The angle that's between the points painted onto the back of your retina is referred to as the absolute disparity. And absolute disparity is a measure of how far an object is away from a particular horopter. And then relative disparity is the difference between the absolute disparity of two objects. Okay, this kind of concept is usually better understood with pictures instead of words. So the first step in understanding how binocular depth perception works is to understand the concept of corresponding points. In other words, you want to make sure you understand that whenever you're looking at a particular point in your visual field, you want to know where that point lands on this eye and on this eye. Okay, so if I'm looking at this pen, at the tip of this pen, I want to know where that image, that little tip there, is being projected on this eye and on this eye, and that tip on this eye and that tip on that eye, on my other eye, are referred to as the corresponding points between the two eyes. It's illustrated here, and one good way to understand what corresponding points are is to imagine that you're projecting some point onto the eye, and let's say that point is A here. And then what you do is you take that picture of the eye with the projection of the point, and then you superimpose that picture on top of the other eye. Notice that when we do that, the point A appears in the exact same spot as in the right eye as it does on the left eye. There's point A there, and there's point A there. And if we put them on top of each other, it looks like one image because it's the exact same. Notice also that point A in this eye is located the exact same distance from the fovea. F indicates fovea, which is the spot in the retina where there's the most cones and rods for seeing. Notice that point A is the same distance from the fovea in the right eye as it is in the left eye. The fact that the corresponding points are equal here and here, and that they're the same distance from the fovea, tells us that point A is in our horopter. It's right there in a particular horopter that we're looking at. Here's an example of the horopter. So this dude is checking out this chick here, right, Julie, and also this tree. Now notice that the tree and Julie are the same distance away from this guy. So if this guy swings his head around and scans along this dash line, anything that he hits in that dash line, any object that appears in that dash line, is going to be in the horopter. Notice that if there was another person here and another tree here, that would be a new horopter, right? So this is the horopter at this distance here, and notice what the horopter looks like on the retinas. So once again, we have this guy's two eyeballs. We have his left eyeball and his right eyeball. And notice also that he's looking at Julie and the tree. And again, notice that Julie and the tree are in his horopter. Notice what happens to the projection of the points inside each eyeball. Julie is being projected to this point here and this point here, the fovea, because he's looking at her. So whatever you're looking at is always projected directly on the fovea. So she's being projected on the fovea. But then look where the tree's being projected. As he's looking at her, the tree's also being projected. It's being projected here at this point, and then the corresponding point here. Notice that the distance from the Julie point to the tree point is the same in this eye as it is in this eye. The fact that those distances are the same tells us that Julie and the tree are in our horopter. They're in the same horopter. If this tree was further back and was in another horopter further away, the distance between here and here would be different, right? I think this one would be very small. Yeah, this one would be very small, and this one would be much larger, which would tell us that they're not in the horopter. But we use that relative, our eyes use that relative distance, this relative distance here, here to here, and here to here, to compute how far away things are. Because like I said, if this tree was behind Julie instead of in the same horopter, if it was further back, then Julie's points would still be here and here because he's looking at Julie, right? But that tree would be up here somewhere, which would mean that this point would probably be really close to Julie, and then this point would probably be completely on another spot. It wouldn't even be corresponding. It would just be on another spot. And that would tell us that that tree is further away. So here's another example, looking at different horopters, essentially, right? So we have, looking at Julie. When I'm looking at Julie, I can tell that Bill is definitely not in the same horopter. He's actually closer to me, because the corresponding point in this eyeball here for Bill is different than this eyeball. Notice that the point for Bill in this eyeball is here on the left-hand side, and over here it's on the right-hand side. What that tells me is that Bill's closer to me, right? Bill is actually a lot closer to me. Let's look at Dave, who's even closer to me than Bill, right? Notice how it goes further out. The point for Dave goes further out, right? And relative to the distance from the fovea, which tells me that Dave is even closer to me than Bill is. So since Julie's point falls here, Dave's point or Bill's point falls here, and Dave's point falls here, we can use this angle of disparity for Dave and angle of disparity for Bill to compute how far away Bill and Dave are, right? Because if the corresponding point for Bill in this eye is right here, but it actually appears here, right? So we can use that disparity, and then for Dave, here's his corresponding point from this eyeball, right? So here's this point here. It's the same point here, but it's actually here. So we can compute this disparity, this distance, to tell us how far away something is. And notice that the greater the angle of disparity, the closer something is to you. So the angle of disparity here between the corresponding point and the actual point of Dave is much longer than the angle of disparity for Bill, which just goes from here to here. Again, that's used to compute relative distance.